Computer Journals. His major is in computer science. He has a PhD in computer science from Ghent University, Belgium, and his expertise in fuzzy rough sets and its application in machine learning algorithms. The title of his talk is Fuzzy Rough Sets, a motivation, definition, and application to machine learning algorithms. Professor Chris Cornelis will join us for Q&A, but his talk is a recorded lecture, so I'm going to play the recorded lecture.
Okay, hello everyone. My name is Chris Cornelis, and I'm an associate professor at the Department of Applied Mathematics, Computer Science, and Statistics here at Ghent University in Belgium. And my research interests are mainly on fuzzy sets and rough sets. And in this lecture, I'm going to give a brief introduction on how to combine them into a hybrid fuzzy rough set theory and how it can be applied to machine learning applications. So the outline of my talk will be as follows. I'll start with explaining what rough set theory is. I'll explain you what inconsistencies in data exactly are and how rough set theory handles them by means of providing lower and upper approximations. Then we'll move on to add fuzziness and end up with the fuzzy rough set theory. So basically, we'll motivate why we need it, specifically to deal with numerical data, where there is notions of gradual similarity and fuzzy membership. We'll give the basic definitions of approximations in this setting, and we'll also discuss some extensions of the classical theory to real-life data, where there typically is a certain amount of noise or outliers to be dealt with. So that will be the robust extension part. And finally, I'll focus on a couple of applications of machine learning. I'll zoom in mostly on classification. In particular, I give an instance-based or lazy learning algorithm, as well as a rule-based algorithm, which is still in progress. And finally, I'll also say a few things about a Python package that we are currently developing at our research group, which is called Fuzzy Rough Learn. Now, to start off, I'll give a simple example. So suppose we have to decide for the customers of a bank whether they're entitled to get a loan or not. And suppose we have some financial parameters about these customers. For instance, we know their debts, their salary, and their investment portfolio. And for a number of customers, in this case 6, we know whether they got the loan, which is 1 as a decision, or they were denied the loan, which means 0 here. So the typical problem in supervised learning is based on this information, on this training data, to train a classifier which for new customers will predict whether a client will get the loan or will not get it. Now, if we look at this data, we immediately can see a problem because number 3 and number 4, they have exactly the same values for all 3 attributes, but they still have a different decision. So that poses a kind of like basic problem for a supervised machine learning algorithm, because how should you teach a student if even the teacher cannot say what's the right answer in a specific situation? Okay, so that is one kind of an inconsistent situation of inconsistent information. And we call instance 3 and 4, we call them inconsistent because they are indiscernible or also indistinguishable with respect to the conditional parameters, with respect to attribute 1, 2, and 3, but they still have a different decision. They belong to the different classes. Now, this kind of inconsistency is not the only one which we will see in practice. For example, if we look at monotone classification, this means that we will also take into account a sort of natural ordering of attributes. For instance, if a person has lower debts, higher salary, and higher portfolio, it's logical that his chances of getting a loan should be higher. But in this case, if we look at number 2 and number 3, we can see number 2 has a higher debts, lower salary, lower portfolio, so he scores worse on all the conditional attributes, but still they got the loan, while number 3 didn't get it. So in this case, we also say that number 3 dominates the instance number 2, but the class of the number 3 is still worse than what number 2 obtained. So in general, we can define inconsistency or consistency as follows. We say that two instances are consistent with respect to some relation, which can be indiscernibility or dominance or something else, perhaps, if they have the relation on the conditional attributes will imply the same type of relation on the decision attributes. So equal on the condition attributes should result in the same decision. Dominating relation on the condition attributes should result in a better decision for the decision, right? So, and this is what rough set theory is all about, to provide approximations of our data which are consistent. Now, if we look at the mathematical framework of that, so as Pawlak, a Polish scientist who proposed this theory in 1982, defines, the goal in rough set theory would be to approximate some concept. For example, the clients who gets the loan, using a set of examples. So that would be the 6 training examples in our example, and an equivalence relation characterizing indiscernibility between instances. So in our example, in the case of the first inconsistency, that would mean that every 2 instances, every 2 clients which have the same condition attribute values would be in the same class, the same equivalence class of the relation E. So if we look at this figure here, we can see that the set A of examples typically will not coincide with a union of equivalence classes, because some equivalence classes will be partly inside of the set A and partly outside. So that's what the inconsistency is in this scenario is about. So what the rough set theory will then do is to provide 2 approximations, a red rectangle called the lower approximation and a green rectangle called the upper approximation. Now, the lower approximation will consist of those instances which certainly belong to the concept. Why certainly? Well, because if we look at these squares, these equivalence classes, all members inside of them belong to the concept. So if you have an object, an instance with a particular set of condition attributes, all the objects with that same characteristics will be inside of the concepts. So that's also written here as a formula. An object or an instance belongs to the lower approximation of A with respect to equivalence relation E if the equivalence class of U is a subset of A. Likewise, the green rectangle will contain instances possibly belonging to A. That means that, well, if an object is in the green rectangle, then there is at least one object in its equivalence class which belongs to the concept. For instance, this rectangle here in the top left position, there is one object inside of A, so this whole block will be added to the upper approximation. And as a formula, this reads U belongs to the upper approximation if the equivalence class of U has a non-empty intersection with the sets A. If we apply that to our example, and so the first kind of inconsistency which I mentioned before, that means so that the set A would be the sets containing instance 1, 2, and 4, because they are the ones that got the loan. The lower approximation will not contain instance number 4. Why not? Well, because it is indiscernible from number 3, which does not belong to the concept. So the lower approximation only has instance 1 and 2. On the other hand, the upper approximation will contain the first 4 instances or clients, because for all of them, if we look at their equivalence classes with respect to these attributes, for all of them, at least one object, one instance will have decision equal to 1. Okay, so that was concerning the first type of inconsistency. Remember, we also had the second type, which was about dominance and about monotone classification. Well, to handle those, An extended theory was proposed by Slovinsky, Greco, and Matarazzo in the beginning of the 2000s years, where the equivalence relation, which is reflexive, symmetric, and transitive, was generalized to a dominance relationship. So basically, we sacrifice symmetry because dominance is not necessarily symmetric. And then we consider, instead of equivalence classes, the so-called dominating sets and dominated sets. So what is the dominated set D plus of an instance U? Well, that is basically just the set of instances which are at least as good as U. So V dominates U. And likewise, we can define the dominated set, D minus of U, as the set of objects V such that U dominates V. Okay, so that's, I think, is intuitively clear. Now we can also generalize the lower and the upper approximation, but the idea of concept first also needs to be generalized, because if we look at monotone classification, we're typically looking at decisions in the form of at least as good as a certain class. So a concept will always be of this form, CT at least larger than or equal to, where CT is a class ranging from 1 to n in general. And an object U will belong to the lower approximation, will be certainly at least as good as CT if D plus U, if all the objects which dominate U, which are at least as good as U, are also have a class at least equal to CT. Likewise, the object will belong to the upper approximation if there is at least one object which is dominated by U, such that it has a classification at least equal to CT. And recall, like dominance is reflexive, that means that each object dominates itself. So in particular, an object can only belong to the lower approximation if it itself belongs to the concept, right? So that's important also to keep in mind. If we apply that to our example, now we can see that the lower approximation will become even smaller because only I1 is not dominated by any object which does not belong to the class, which was denied the loan. Okay, so in this sense, the lower approximation would contain only instance 1, while the upper approximation in this case will contain the objects from 1 till 4. To our financial parameters, then number 5, but still they got the loan, but number 5 didn't. So we can say that there's a kind of partial inconsistency in here. Now, in order to deal with that, to extend rough set theory to handle that kind of partial inconsistencies, we can extend it with fuzzy relations, relations that will express degrees of similarity, to what extent are two objects similar to each other, or dominance, to what extent is one object better or at least as good as another one. And this will lead us to the definition of fuzzy rough lower and upper approximations that we'll get to in the next couple of slides. But before that, I need to explain how we model gradual indiscernibility and dominance. And to illustrate that, let's focus first on a single numerical attribute of a data set, for instance, that from the previous slides. And with this, we will define a corresponding fuzzy indiscernibility relation, EA, which for two objects, two instances U and V, will give a number between 0 and 1 expressing how indiscernible they are. 0 means that they're totally different, while 1 means that they cannot be discerned from each other. They're equal as far as this attribute is concerned. Now, in order to measure that, we can go about in different ways, but a very common way is to focus on distance. And what is the easiest way to compute distance? Well, is just to calculate the absolute difference between the attribute values AU and AV. We can normalize that by dividing by the range of the attribute. and we can multiply that by using some parameter gamma greater than 0. The role of this parameter will become clear immediately. Now, this will give us a distance. Since we're talking about indiscernibility, we should take 1 minus this ratio. And in order to make sure that the result is between 0 and 1, we take the maximum of 0 and this expression here. So at the bottom of the slide, you can see how this is interpreted. For example, suppose that the attribute A has a range from 0 to 1, and that object V has a value of 0.5. And let's fix the parameter gamma to 4. Then you can see that if we let the value of AU range away from 0.5, lower or larger, greater, then we can see that the degree of indiscernibility will go down up to the point 0.25, 0.75, where the degree will be equal to 0. So the two objects will be totally discernible. And this slope of the triangle here can be controlled by means of this gamma parameter. So this is just one way, just to give you an intuitive idea of how indiscernibility, fuzzy indiscernibility, may be modeled. So far, we only dealt with one attribute. If we take into account more than one, for instance, all the attributes in our data set, what we typically do is take a minimum or a different kind of aggregation of the individual degrees of indiscernibility. So this min A here refers to taking the minimum of the individual degrees of indiscernibility for each attribute. And if we apply that to our example and the given relations before, then we end up with a matrix like this, which for every pair of instances gives you their degree of discernibility. So note that on the diagonal, we have always 1 because an object is there. Now we will evaluate the degree to which one value is higher than another value. And the formula which we can use for this is very similar, looks very similar. It is a bit more complicated than the one for indiscernibility, but here in the figure down below, we can see clearly what happens. So if A of V is still 0.5, then a value A of U will dominate it to a degree 0 if AU is smaller than 0.25. Then it increases until it becomes 1, starting at 0.5. So note that there is a segment where A of U is still smaller than A of V, but it dominates A of V to a certain extent because of this formula. And again, we can take the aggregation over all the attributes by taking the minimum or another kind of aggregation function, and we end up with again, a matrix which is still has ones on the diagonal because of reflexivity, but is no longer symmetrical. So far, we focused on making the indiscernibility or the dominance relation fuzzy, but nothing stops us from doing the same to the concepts. So instead of using crisp classes as concepts, we can use fuzzy sets. And one scenario where this intuitively makes sense is when we deal with regression problems. In regression problems, the decision attribute is going to be a numerical value. For instance, in this simple example of predicting apartment prices. So we have a number of criteria about apartments, and we can try to decide how much this apartment would cost. So instead of exactly predicting those values, we could also try to approximate the concept expensive apartments. So the decision attribute in this case would reflect the degree between 0 and 1 to which an apartment is considered expensive. And the goal in general, what it all comes down to is we need to establish how we will compute, define lower and upper approximation of a fuzzy sets, some concepts, under a fuzzy relation, either dominance or indiscernibility. And for that, we will use some of the machinery that fuzzy logic gives us. So in order to define fuzzy rough sets, we go back to the beginning, to Pavlak rough sets. So to the condition for belonging to the lower and upper approximation of an element to a set based on some equivalence relation E. So that meant for the lower approximation that the equivalence class should be fully inside of A. And if we break that down into a logical condition, it means that for every object V in the set of all objects, if V and U are indiscernible, then V must belong to A. Likewise, U belongs to the upper approximation if the equivalence class of U has a non-empty intersection with A, meaning that there exists some object V in U such that V and U are indiscernible, belong to E, and V is an element of A. So if we look at these two conditions, the for all and the exists, we can see, or we can try to extend those to fuzzy logic. So we have here a logical implication, here we have a logical conjunction, and we have those two quantifiers for all and exists. So we are going to extend that now to fuzzy rough sets, where the equivalence relation will become a general fuzzy relation, either fuzzy indiscernibility or fuzzy dominance. And the set A, the concept, will now be in general a fuzzy set. Okay. Now, in order to do that generalization, we need operations to generalize the implication and the conjunction. And for those of you who are familiar with fuzzy logic, there is not one way to do that, but there's whole classes of logical connectives available for that. For instance, for implication, we have a class of fuzzy implications, and for conjunction, we can use so-called triangular norms, or shortly T norms. So basically, those are binary operators which take two values in the unit interval in 0, 1 and give you back one value, which gives you the value of logical implication or conjunction. And for the quantifiers, the for all quantifier is typically replaced by the minimum over the set U, and the existential quantifier is replaced by the maximum. So what we get is two fuzzy sets, lower approximation of A under R and upper approximation of A under R, to which an element U belongs to the degree which is shown here on the right. For the lower approximation, we take the minimum of all the implication values of RVU, the degree to which V and U are related, and the membership of V to A. And the same for the upper approximation with the maximum and T norm. So to help you understand these concepts a little bit better, I've applied them to our toy dataset of obtaining a loan. Whereas fuzzy implication and fuzzy T norm, I've used the operators of Lukasiewicz, which are defined as here. So IXY is the minimum of 1 and 1 minus x plus y, and TXY is the maximum of 0 and x plus y minus 1. But in general, you can use any combination of a fuzzy implication and a T norm. And so what we do is we plug those operators into the formulas for the lower and the upper approximation. And remember that for the fuzzy relation, we use the relation, the indiscernibility relation that we derived before from the data based on the absolute differences between attribute values. So we use this matrix here. And the concept A, the fuzzy set to be approximated, will be just the classical set containing of objects. You can notice, for example, that instance 1 and 2, before they belonged fully to the lower approximation in the classical case, but now because of taking into account the fuzzy inconsistencies, their membership degree becomes lower. And similarly for the upper approximation, we can see that the first 4 clients are still fully contained in it, but also client 5 and 6 belong to it to a albeit low degree are also included in this upper approximation. Now, before I move on to the applications, there is one final important subject which I need to discuss, which is the sensitivity to noise of the Fuzzy-Ruff lower and upper approximation. Now, if you look at these two formulas, which determine the membership to the lower and the upper approximation, you can see that the use of the minimum here and the maximum here will cause a change in a single element to have rather big consequences for the results. For example, for the lower approximation, it is sufficient that there is one object V which is completely similar to U, so RVU is equal to 1, and V does not belong to A at all, so A of V is equal to 0. In that case, the result will be equal to 0. In the same way, the membership to the upper approximation will quite easily become 1 because of the use of the maximum here. And this may result in a reduction of the usefulness of the approximation, because if the lower approximation is almost empty and the upper approximation contains almost every element, then they are not very interesting in machine learning algorithms. So this is a problem which is not only present for Fuzzy-Ruff sets, but also for Rush, is to make sure to adapt the definitions so that they do not depend on just one element. And also in our group, for several years, we've worked on different Fuzzy-Ruff set models, and the one which I will discuss in these slides, in this presentation, is called the ordered weighted average based Fuzzy-Ruff set model, so OWA. So what does OWA stand for? Well, I think everyone is familiar with the weighted average of a number of values, real values, by means of a weight vector. So we have weights from 1 to n such that their sum is equal to 1. Now, in the ordered weighted average, what we do is before we apply the weighting, we first order the values in A from the largest till the smallest, right? So, and then we apply the weights to these ordered positions. Very simple example to illustrate that. Suppose we have 4 values here and we have 4 weights. So the OWA with these weights and these values will be calculated by first ordering the values from large to small. So 0.7 is multiplied with the first weight, 0.2 with the second, and then 0.1 with the last 2 weights. And the sum of all those calculations, those multiplications, will be the OWA value in this case. Now, what makes the OWA operator interesting is that it covers a lot of other cases as special cases. So for instance, the minimum, which we already encountered, is a special case where we give all the weights to the last element. So all the weights are 0 except the last one, which is equal to 1. In the same way, the maximum is a special case where we give all the weight to the first element. And also the classical average is a special case where we just distribute all the weights evenly among the different positions. Now it becomes interesting when we consider so-called soft minima and soft maxima, like the ones here. So for instance, additive weights, you can see that the weights will linearly increase from small to large, giving the highest weight to the last element, but also giving some weight to the elements before that. And exponential weights do the same, but the increase will be more drastically in that case. So that makes it possible not just to take into account smallest element for the lower approximation, but also some of the elements before that. And this is used in our OWA-based Fuzzy-Ruff set model, where we will replace the minimum and the maximum for the lower and upper approximation by 2 OWA weight vectors. So notice that the implication and the t-norm still appear in this OWA-based rough set model, but the minimum and the maximum have been replaced by a soft minimum and a soft maximum, respectively, in order to take into account more than just one element in computing the approximations. Now, of course, the choice of the OWA weight vectors will determine the performance of the model, so it has to be chosen wisely. In general, some default values like the linear weights or the exponential weights from the previous slide can be used. But in some cases, it's also useful to tune the OA weight vectors based on the data set at hand. The next slide shows some of the main application domains of fuzzy rough sets in machine learning. And as you can see, this basically covers the whole spectrum ranging from supervised learning over unsupervised and even semi-supervised learning. And various researchers all over the world have contributed different algorithms for these domains. Now, perhaps one of the most emblematic applications of fuzzy rough sets and also of classical rough sets would be feature selection. And here the idea is that we want to remove attributes or features as long as by doing so, we do not add additional inconsistencies in data with respect to indiscernibility or dominance, as we discussed at the beginning of this presentation. I'll give you two types of algorithms, one instance-based and one rule-based. The first algorithm is called Fuzzy Rough Nearest Neighbors, or FRNN for short. And here the idea is that in order to perform classification, first we construct the lower approximation and the upper approximation of each decision class C of our problem. And then when a test instance Y arrives, we compute its membership to these approximations, and we will assign the test instance to the class for which the average of these two numbers will be the highest, so the argmax. And in other words, upper approximation as clues to decide to which class an object should belong. Now, as the name FRNN implies, it's closely related to other nearest neighbors approaches, such as, for instance, traditional KNN or its fuzzy variant, fuzzy nearest neighbors. And we can even show that under specific conditions, the results of FRNN will be the same as the ones obtained by just looking at the first nearest neighbor of the test object. And this happens specifically when we use the minimum for the lower approximation, the maximum for the upper approximation, and we use specific choices for the d-norm and the fuzzy implication. But in general, specifically when we use the OA-based variant, which I discussed in the previous slides, the results will be different, and the intuitive understanding is also different because FNN and KNN will use a weighted voting based on the classes of the nearest neighbors, while FRNN will look at the objects certainly belonging to a class, possibly belonging to a class, and using all this information as clues to determine the class membership. Computational complexity. And given the fact that computing the lower and the upper approximation of decision classes can be a very costly operation, especially in large data sets, we typically apply a number of optimizations to the basic procedure. And one of them is, for example, that instead of using the full training set, we restrict ourselves to the nearest neighbors of a test instance Y to compute the membership to the lower and the upper approximation. And this already gives a rather significant speed up, which can still be improved by not looking at the exact nearest neighbors, but by using a heuristic for finding approximate nearest neighbors. And a good thing about these optimizations is that while they make the algorithm run a lot faster, they do not sacrifice almost anything in terms of classification accuracy. And speaking of accuracy, we recently conducted a large-scale experimental study in which we were able to show that FRNN significantly performs better than both KNN and fuzzy nearest neighbors, which kind of makes FRNN like the best choice for a lazy learning algorithm. Now you might wonder why we still need lazy learning or instance-based algorithm in a time where there are so many powerful classifiers based on deep learning, on random forest, and so on available. And my answer to that would be that they serve very well as explainable or interpretable machine learning models. And to illustrate that, I would like to mention a use case that we developed together with my PhD student, Olga Kaminska, in which the goal is to detect the level of presence of an emotion in tweets, so in short sequences of text. Neighbors in our training set, we will see that all of the nearest neighbors also have this word offended, and it actually helps us to explain why the prediction of intensity, anger intensity of 2 was obtained here. Now, if we compare that to a deep learning approach, it would also be able to correctly predict the level of intensity, but since it's a black box, it's not able to explain you why that prediction was generated. So in that sense, nearest neighbor approaches can give benefits. Let me also mention that a number of adaptations of the basic FRNN algorithm were developed for specific kinds of data. For example, for imbalanced data, this is the case, for instance, when you need to diagnose a very rare disease. So most of the patients in a hospital would not have this disease, but a small subset of them do. So in this case, you need to adapt your classifier by taking into account this imbalance. And the way we did that with fuzzy rough nearest neighbors was to use two different weight vectors. So one OVA weight vector for the majority class and another one for the minority class, which is the interesting class that your version was later extended to a multi-class version where we used 1 versus 1 ensembles to perform the classification. Apart from this, we also focused on multi-label data, where the idea is that one object can be associated with many labels. For instance, you can have a painting with multiple objects present in it. On the other hand, multi-instance data, this is kind of the opposite case where one object has multiple feature vectors, multiple configurations of the same object, but there is only one class label. So in both cases, the classification problem is more complex because for multi-label, we need to compare label sets instead of single labels. And for multi-instance, we need to compare multi-sets of feature vectors, which require other kinds of techniques for comparison. Another kind of classifiers based on fuzzy rough sets are rule induction algorithms, and this is still very much a work in progress together with my PhD student Henri Bollard. The idea is that we want to extend existing rule induction algorithms based on classical rough sets to fuzzy rough relations. So for instance, if we look at our toy data set again, from the first instance, we could derive a rule such as if the debt is around 2,200 and the salary is around 4,200 and so on, then the decision is equal to 1, where the approximate equality can also be replaced by approximate dominance if the debt is more or less smaller than 2,200 and so on. So this is again an example of an interpretable or an explainable machine learning model, but there are a number of important challenges here. Of course, we don't want every object in the training data to generate a rule. That would be simply too many rules. So we need a way to find prototypes, which are some given instances of the database, or granules, which are constructed, which take together different instances together to limit the number of rules. And on the other hand, we also want to make the rules as general as possible. So if we can skip from certain rules specific attributes, that makes the rules applicable to a larger class of objects, and this is of course beneficial. Finally, let me mention that implementations of most of the algorithms that I have discussed in this lecture, as well as other algorithms, are publicly available in a machine learning library called Fuzzy Rough Learn. It's based on scikit-learn. It was developed by my ex-PhD student, Oliver Lenz, and currently it's still being updated, but feel free to test it on your data. If you have any feedback for us or questions, don't hesitate to get in touch. This very brief introduction to fuzzy rough sets, I was able to convince you at least of the potential that they hold for machine learning purposes. Now, if you're interested and want to learn more about this work, then I invite you to have a look at the website of my research group called Computational Web Intelligence, or CWI, here at Ghent University, where you will find the full text versions of most of the references which I've mentioned during the talk, as well as many other papers which we've published over the years. Also, if you have any kind of questions, feedback, feel free to contact me by email. And finally, let me mention that if you're interested to do some of your own research in this domain, that there's still a lot of open problems to be solved. For instance, I'm thinking about regression, semi-supervised learning, finding particular shapes of similarity or dominance relationships and inducing them from data sets. Also, the link with granular computing is interesting. So I've been talking mainly about lower and upper approximation, but in this framework, we can consider also other kinds of approximations called granular approximations, which are also something which still needs a lot of further research. So if you're interested, don't hesitate to contact me. And finally, I would like to thank you for your attention.
That was a talk from Professor Dr. Chris Cornelis. I would like to thank him for his insights on fuzzy sets, fuzzy rough sets, and its application to machine learning sites. Unfortunately, Professor Cornelis is not with us for question and answer session. He might join us on some of our weekly seminar series later on. And he just sent an email to us that if anyone have any question, they can send him an email. I will provide the email address of Professor Cornelis in the discussion section right now after in the other talk. So now I would like to call our next participant, which is a PhD scholar at RIPA International University. He's one of our he's our PhD scholar from our pioneer batch, Ansar Abbas. He's a student of Professor Dr. Abdul Khalik, and the title of his talk is Chaotic Dynamics of Three Species Food Chain Model. Ansar Abbas.
Thank you, Doctor. Myself, Ansar was a PhD scholar. Sir, can you hear me?
Yes, we can hear